So this recording is for Further Maths Core Pure 1, Chapter 1, Complex Numbers. It covers complex numbers from the perspective of how to add, subtract them, what a complex number is, solving equations with real coefficients, which is different to solving them when you have complex coefficients, and for quadratics, for cubics and quartics. You'll also see in Chapter 2 that there's a geometric view of complex numbers, which uses an Algan diagram, and essentially you can view a complex number as a two-dimensional vector, which is a way I'd like to visualize them. And if you want to look at that, you might want to have an early look at Chapter 2, but we'll deal with that later. So what is a complex number? Well, you can think of a complex number as arising in a quadratic from the situation when the discriminant b squared minus 4ac gives you a negative, which in the past we've said means that it has no real solutions. But now we can consider that if we invent a number called an imaginary number to be the square root of -1, this is the only number we need to add to then be able to solve quadratics where the discriminant can be negative and can have any value that is negative. It doesn't have to be just the square root of -1. This was actually done quite a long time ago, before even maths sorted out things like negative numbers, zeros, etc. So it has quite a long history, and it was used to solve equations. And you can do a little bit of the history here. And so what is I? I is the square root of -1, and I is called an imaginary number. And if you multiply it by a real number, you still have an imaginary number. So I is an imaginary number, 3i is an imaginary number, minus 2i, I times pi, I times root 2, etc., etc. A complex number is where you have a sum of a real number, a in this case, and an imaginary number as in general b times I. And if you add those two together, you get a complex number. And in terms of vectors, you can think of this as the real part. The a is the real part, and b is the imaginary part. So a is, if you like, is the component in the x direction, and b is the component in the y direction. But more of that later. So it is possible to write down a complex number always in this form: a real part plus a real number times the I, which is together called the imaginary part. So we say A is the real part and B is the imaginary part of the number, if you like, coefficients of your two dimensions of your two-dimensional vector. Some notational comments here, which I'll skip over, and some applications of complex numbers, which you're welcome to look at. Fractals is a really neat one. I think there's a slide later on about that one. And if you study complex numbers, if you study computer science, this actually is quite a nice little project. I've supervised one student who actually created a Mandelbrot set for his computing project. Okay. So how are we going to do something like the square root of -36? Well, you can do that using I by factorizing the 36 into 36 times -1. And then the square root of 36 is 6, and the square root of -1 is I. And so if the square root of -1 is I, then the square root of -36 will be 6i. And we can do other questions in the same way. If you multiply 2i by 2i, you get 4i squared. And if the square root of -1 is I, then I squared would be -1. And so 2i squared will be 4 times -1, it will be -4. And so 2i is the square root of -4. Or you can think of it as 4 times -1. The square root of 4 is 2, the square root of -1 is I. Either way. Likewise, root of -7 is going to be root 7 times I. If you multiply this out, you get root 7i times root 7i equals 7i squared, which is -7. When you have complex numbers, we want to be able to add them, multiply them, divide them. So how do we add them? I think of them as vectors, and so we just add the components, the real part to the real part, the imaginary part to the imaginary part. When you multiply them, you can think of the usual multiplication. So here you've got minus 3 times 2, which is minus 6, minus 3 times I, which is plus 3i. And if you have another I here, you get 4i. So treat this as you would any expression and just multiply it out. And for this last one, if you have 10 plus 4i divided by 2, we just divide the real part by 2 and the imaginary part by 2 to get 5 plus 2i. And the purpose of this is to make sure that if we have an expression involving complex numbers, then that complex number can always be written in the form a plus bi. And you should be able to do this. This is largely what this chapter is about. Okay, so solving equations. If we have something as simple as z squared plus 25 equals 0, what do? Well, we just rearrange, get z squared equals minus 25, take square roots, and so we get z is plus or minus the square root of minus 25, which means that z is plus or minus 5i. And if you want to check it, if you square z, you get 5 squared, I squared, and 5 squared is 25, and I squared is minus 1, so you get minus 25. How about something like this? Well, you can use the quadratic formula. You can complete the square, and either of them should give rise to the fact that the solution of this is z equals minus 3 over 2 plus or minus square root of 11 over 2i. Notice this again is in the form a plus bi, but there are two complex numbers that satisfy this. Okay? And this leads us to something interesting about quadratics, that they always have two solutions. In the past, we said they had two real solutions, or one repeated real solution, or no real solutions. Well, now, when it has no real solutions, we see that it has complex solutions. If you want to do this by completing the square, you'd simply say this could be written as z plus 3 over 2 all squared minus 9 over 4 plus 5, and then moving the minus 9 over 4 plus 5 onto the other side, and then square rooting, we end up with this as well. You might want to try your hand at that. Okay, so do some exercises. Once we've worked with I a little bit, you should be able to do these kind of questions. So what's I cubed? I cubed is I times I times I, but we know I times I is minus 1 because I is square root of minus 1, so I squared is minus 1, worthwhile remembering that. So now I cubed is going to be minus 1 times I, and it's minus I. So again, we've written a complex expression as a plus bi, where a is 0 in this case. I to the 4, well, I to the 4 will be I to the 2 times I to the 2. I to the 2 is minus 1, so this could be minus 1 times minus 1, which is 1. And so we know what I is, we know what I squared is, it's minus 1, we know what I cubed is, we know what I to the 4 is, and notice that I to the 4 is 1, so I to the 5 will be 1 times I, and so it'll cycle. And you see this note here, if you take any power of I, you're going to get I to the 1 is I to the 2 is minus 1, I to the 3 is minus I to the 4 is 1, I to the 5 will now be back to I to the 6 will be minus 1, and so on and so forth. So if we do I to the 101, we notice I to the 4 to the 25 times I, and I to the 4 is 1, so this will be 1 to the 25, which is just 1, and so I to the 101 will be just I. So again, we're able to write this in the form a plus bi. Okay, and this one here, if we use expansion of ab to the n is a to the n, b to the n, which still works with complex numbers, we get this is 3 to the 5 times I to the 5. 2 to the 5 is 243. I to the 5 will be I to the 4, which is 1, times I. So this is 243i. Multiplication, well, we do this as in we do with real binomials. We just multiply them out. So the 2 multiplied by the 3, the 2 multiplied by minus 2i, the 3i multiplied by the 3, and the 3i multiplied by the 2i. When you multiply the imaginary parts together, you get an I squared, which gives us the real part. So you're going to get 4 terms, 2 of them real and 2 of them imaginary. And when you collect them together, you get a complex number. And likewise, if you're squaring a complex number, you could just think of it as the same thing, real times real, imaginary times imaginary, real times imaginary, and imaginary times real. So you get your 4 expressions, which can simplify down into A plus BI form. Okay, so here's an old paper question. Z equals 2 minus 3i. Show that z squared equals minus 5 minus 12i. Well, we can simply square z. So we write 2 minus 3i multiplied by 2 minus 3i, and you should be able to get that. And here, this question, we want 1 plus I cubed, so we just do 1 plus I times 1 plus I times 1 plus I. Or you can use the binomial, which still works. So 1 plus I cubed would be 1 plus 3 times 1 squared times I, plus 3 times 1 times I squared, plus I cubed. And then if you sort those out, you end up with minus 2 plus 2I. Okay, Mandelbrot, I'll leave you to read about this. I'm not going to go through it now. But if you're interested, come and have a chat with me about it if you want. Complex conjugation. This is really quite important. It's so important that you have a special symbol for it. So if a complex number is A plus BI, its complex conjugate is written as A minus BI. So in this case, if X is 3 plus root 2, because a complex number is usually written as Z, but it can be written using any other variable. So if X is 3 plus root 2i, then X star is 3 minus root 2i. I'm sorry, but the I is missing here. I'll have to change that. So it's X plus X bar. It's going to be 6. X times X bar is going to be 7. Oh, I see. It's actually meant to be without the i's here. But for complex numbers, there would be i's. But if you do it even with the real numbers, you still get this. And now if you do it with complex numbers, let's have a look at that. So if we now have a complex number, 3 plus 2i, and then its complex conjugate will be 3 minus 2i. Okay, I haven't used this notation for 3 plus root 2 and 3 minus root 2, so that's interesting. But it definitely is used with complex numbers. So what's z plus z conjugate? Well, what you notice is that the imaginary bits cancel out, and so you just get the real bit. And that's the case also when you multiply a complex number by complex conjugate. So if you try this out, you get 3 times 3, which is 9, 2i times minus 2i, which is minus 2i squared, which is minus 4i squared, and the I squared gives me minus 1, so it's plus 4. And then the 3 times minus 2i and the 2i times 3 cancel out, and so you just get a real number. So really important to notice that when you add a complex number to its complex conjugate, you get a real number. When you multiply a complex number by complex conjugate, you get a real number. So this is really useful. And we'll see a little bit about why when we come to the Argand diagram, if you want to see it geometrically. So this important result is here. Okay. So please make a mental note of that, or even a physical note of that. So this enables us to divide complex numbers. How so? Well, suppose you want to divide 5 plus 4i by 2 minus 3i. And whatever we get, that answer means that if we then multiply that answer by 2 minus 3i, it should give us 5 plus 4i. Just in the same way as you divide 16 by 8, you get 2, means that 8 times 2 is 16. So what we would have done when we're doing surds is we multiply a surd like root 2 minus root 3 by root 2 plus root 3. Well, in a similar way with complex division, we multiply by 1, but taking the complex conjugate of the thing we're dividing by, the denominator. So 5 plus 4i over 2 minus 3i, if you want to work out what it is in A plus BI form, you multiply the top and the bottom by the complex conjugate of the bottom. So if you now look at what you get at the bottom, because you have a number times its complex conjugate, you're going to get a real number. So in this case, you're going to get 2 squared and minus 3i squared, which is going to produce 4 and plus 9. And at the top, you get a number, which you work out, and then you divide each of those simplified A plus BI number at the top by the real number at the bottom, and you have your answer as a real number. And so we're using the fact that a plus bi times a minus bi, so complex number times its complex conjugate, always gives us a real number. And it's used so much, it's worthwhile realizing it. When you multiply a plus bi by a minus bi, you always get a squared plus b squared. Okay. Notice that with the real numbers, you get a squared minus b squared, but here, because you have I squared, the I squared part produces -1, which changes the minus b squared into plus b squared. You can do this on your calculators. I don't usually bother, but maybe have a look to check your answers by using your calculator. Okay, so here's a typical exam question. So you have Z1 equals 3 plus 2i, and you want to work out Z2, where you take 12 minus 5i and divide it by Z1. So if you actually write that out, you want 12 minus 5i divided by 3 plus 2i. How do we work it out? Well, we multiply it by the complex conjugate of the denominator. If you do that, the bottom becomes a real number, simplify the top, and you end up with 26 over 13 minus 39 over 13i, which means you again are able to write this as a plus bi complex number. And notice that if we multiply 2 minus 3i by 3 plus 2i, you should get 12 minus 5i. So that would be a good thing to do, to just check that the division works. Okay, another question here. So z equals x plus iy. Find the value of x and the value of y is such that 3 minus I times the complex conjugate of z plus 2iz equals 9 minus I. So what I would do here is substitute z with x plus iy, and substitute z star with x minus iy, and then work it out, which is what they've done here. So 3 minus I times x minus iy, 2i times x plus iy equals 9 minus I. You multiply that lot out, and then what you do is you can compare coefficients. So here on the left-hand side, the real part is 3x minus 3y, and on the right-hand side, the real part is 9. And on the left-hand side, the imaginary part is minus 3y plus x, and the imaginary part is -1. It's a bit like vectors. So if you have a two-dimensional vector, you can compare the horizontal component with the horizontal component on the other side, and the vertical component with the vertical component on the other side. With complex numbers, two complex numbers can only be equal to each other if the real part equals the real part and the imaginary part equals the imaginary part. So in this case, once we've simplified this and we collect the terms, we can see this is the case. You could have brought the 9 and minus I onto this side and simply said it's equal to 0, in which case you could have got equations with the real part being 0 and the imaginary part being 0. But you can also just leave this 9 minus I on this side and compare coefficients. So in this case, x equals 5 and y equals 2. So we know what z is, and of course we know what z star is. It'll be 5 minus 2i. So solving quadratics, so we can of course factorize them, but the converse is true from the theorem. We know that actually we work out an equation that provides those roots. So if -5 and 1 are roots, then x plus 5 and x minus 1 are factors, and you can get the quadratic equation with those roots. And this is quite useful. So if you have roots alpha and beta or quadratic, then we can work out that the quadratic, if you want to get it in terms of 1x squared, will be x squared minus the sum of the roots plus the product of the roots. Sorry, x squared minus the sum of the roots times x plus the product of the roots. So the coefficient of the x is minus the sum of the roots, and the constant is the product of the roots. This actually works with complex numbers as well. Now, here it's saying, what happens if one of the roots of a quadratic is 3 plus 4i? Do we know what the other root is? And the answer is no, we don't. But what is meant by this slide is, do we know the other root if the quadratic is a quadratic with real coefficients? And if it has real coefficients, then it basically means that the two roots have to be either real, or if they're complex, they have to occur as complex conjugate pairs. So the other root has to be 3 minus 4i if the coefficients of the quadratic are all real numbers. Okay, and that's what it's saying here. So there's a proof here about how we can get that. The first proof is basically saying if we have a quadratic with real coefficients, okay, so A, B, and C are all real numbers. If they're complex numbers, then what we've said about complex conjugate pairs is not true. But if they're all real numbers, if A, B, and C are real numbers, and B squared minus 4AC here ends up being a negative, that's fine. We're going to get X as a complex number. And notice it's going to be a real part plus or minus an imaginary part. And that basically means we're going to have a real part plus, so I can get something plus something I and something minus something I. And so notice that we're going to get two complex numbers, one of which is the complex conjugate of the other. Another way of seeing this is that if we use this fact that when you multiply out x minus alpha times x minus beta, you get x squared minus alpha plus beta x plus alpha beta. And you work your way through and say, well, if these are going to be real coefficients, then alpha plus beta must be real. And if we let alpha be a plus b, a1 plus b1i, and beta be a2 plus b2i, where a1, b1, a2, b2 are real numbers, because you can always write down a complex number as a real number plus a real number times I. Then the sum of those two will be a1 plus a2 plus b1 plus b2i. And if alpha plus beta here is real, that means b1 plus b2 must be 0. And so b2 must be the negative of b1. And then likewise, if we assume that alpha beta is going to be real, but we know that b2 equals minus b1, if we multiply alpha times beta in these forms, put them into the real part and the imaginary part, replace b2 by minus b1, and then say the imaginary part must be 0, because remember that this coefficient here we're told is a real number, then that means that b1 times a2 minus a1 is 0, which either means that b1 is 0, which basically means it's a real number, or a2 equals a1, which again means that a1 equals a2, and so we have a1 equals a2 and b2 equals minus b1. So one of the roots is a plus bi, and the other root is a minus bi. So in other words, they occur as complex conjugate pairs. Yeah, that takes a little bit of looking at. Look at it with your leisure, but either of these prove that if you have a quadratic equation with real coefficients, then the roots, if they're complex, have to occur as complex conjugate pairs. So if one of them is a complex number, the other one has to be its complex conjugate. And we can use that. So given that 7 plus 2i is one of the roots of a quadratic equation, okay, with real coefficients, what's the other root? Well, it's the complex conjugate. So if 7 plus 2i is a root of quadratic with real coefficients, then 7 minus 2i must be the other one. How do we work out the quadratic equation? We can do it the long way by saying one of them factorized is 7z minus one of the roots, and the other one is z minus the other root. Multiplying all that out, we get that the quadratic is z squared minus 14z plus 53. Quicker way of doing it is to use the fact that the quadratic can be written as z squared minus the sum of the roots plus the product of the roots. And so you can just add the two roots together and you get 14. And so the minus the sum of the roots is minus 14. And the product of these two, if you multiply them together, you get 7 squared, which is 49, and 2 times 2, which is 4, particularly when you take into account of the I squared, which gives you 49 plus 4, which is 53. Or if you wanted to do it, another way of doing it is to say, if the roots are 7 plus 2i and 7 minus 2i, that basically means that x or z equals 7 plus or minus 2i. And then if you subtract the 7, you get z minus 7 equals 2i. Square both sides, and you end up with this. Okay. In other words, you're completing the square backwards. So that is a third way of doing it. So an exam question here. 2 minus 4i is a root of this quadratic. Notice that here we're told p and q are real. Okay. And so the other root has to be a complex conjugate of 2 minus 4i. So that's a nice, simple answer. And then if you want to get what P and Q are, you can use either of the methods. They've used the slow method here, or simply saying, okay, so it's going to be, the quadratic's going to be z minus one of the roots, z minus the other root, multiply it out, and you get this. Or you can use the other two methods that I showed you in the previous slide. Okay, what about roots of cubics and quartics? Well, if you think about the graph of a cubic, essentially you're going to get one of these three situations. So on this one, you can see because it crosses the x-axis in three places, this cubic is going to have three real roots. This cubic has one real root, and now, as I kind of suggested, but it's actually the case, that any polynomial of degree n will have n roots. So a quadratic will always have two roots, a cubic will always have three roots. Okay, so the answer to all of these is that there will be three roots. In this first one, you have three real roots. In the second one, you have one real root, and so you have two complex roots. And if your cubic has real coefficients, only if it has real coefficients, then we can say that the two complex roots will be conjugates. And the third case here, we have three real roots, well, two really, but to make our statement that a polynomial of degree n always has n roots, we kind of cheat by saying that here we have two real roots. So here we have three real roots, one real root here, and a repeated root here. And this is one of the reasons mathematicians talk about this being a repeated root. Okay, what about quartics? Again, degree 4, so it's going to have 4 solutions. So here it crosses twice, and if the quartic has real coefficients, again, it has to have real coefficients for the statement about complex conjugates to be true. The statement about having 4 roots will always be true, but complex conjugates will only be true if they're real coefficients. So for this quartic, we have 2 real roots, and so if it has real coefficients, the 2 complex roots will be complex conjugate pairs. If it had complex coefficients, it would have 4 solutions, 2 real solutions, and 2 complex solutions, which might not be complex conjugate pairs. But if the quartic has real coefficients, it'll be 2 real roots and 2 complex roots, with the complex roots being complex conjugate pairs. Okay, here we have 3 real roots, but notice this is a repeated root here, so actually we have 4 real roots, 2 of which are the same root. And here, and notice there are no real roots, and if we have the quartic has real coefficients, that means that there can be 2 pairs of complex conjugate roots, with giving us 4 roots. And this does carry on to quintics and so on, okay? But we only really need to look up as far as quartics. So, exam question that looks hard, but actually it's quite easy. Given 3 plus I is a root of the quartic equation given here, notice that although using z, all the coefficients are real. In fact, here they're integers, but they don't have to be integers. They can be decimals, surds, whatever, but they have to be real numbers. Because they're real numbers, if 3 plus I is a root, then 3 minus I, its complex conjugate, must also be a root, which basically means that we now know that z squared minus 6z plus 10 is a factor of this quartic, and then either by long division or by inspection, we can work out the other factor, because what we did with the long division, polynomial division, etc., all still works. It's just that we might now have x or z being a complex number. So here, if we work out what the other equation is, we get 2z squared plus 9z minus 5, and then solve that, and we end up with the solutions 3 plus I, 3 minus I, and then solving this quadratic here, we get a half and minus 5. So these are then the 4 roots of this quartic. Complex conjugate pair and 2 real solutions in this case. Another question, very similar. Show that z squared plus 4 is a factor of this. Well, we can do that by getting the other factor and using long division or inspection to work out the other quadratic. And then we can get the roots of this one by just rearranging. And the other one, because it'll be a quadratic, we can then use quadratic formula whatever method we like to get its roots. Okay, so yeah, factorizing this, putting in z² + 4, which is a known factor in here. So the author of this PowerPoint likes to do it by inspection. So you can see that this will be z². You can see this will be 17. So it's just doing a bit of work to work out the AZ, and they've done it by comparing coefficients. But you can do it by long division, whichever method you like. And once you've got this is z² - 2z + 17, you can now look at using the quadratic formula or completing the square on this, and you then get that the roots are 1 ± 4i here. So notice that because this is a quartic, and we have 4 roots, they occur in complex conjugate pairs. So plus or minus 2i from the z² + 4 equals 0, and 1 plus or minus 4i from the z² - 2z + 17 equals 0. So 4 roots, all complex, but because the coefficients are real, they occur in complex conjugate pairs. Okay, given that 2 and 5 + 2i are roots of this equation, it's a cubic. So this is a real root, this is a complex root, and we're told that c and d are real numbers, so this has got real coefficients, and therefore the 5 + 2i, if that's one root, the other root must be 5 - 2i, because it has 3 roots, a real root and 1 complex root, so the other complex root has to be the complex conjugate of 5 + 2i. So that's a nice easy answer. And then write down c and d. Well, all we have to do is multiply out this factorized, so we have x minus one of the complex roots, x minus the other complex root multiplied out, or you can use sum of the roots and product of the roots to get this equation here. And then if you multiply that out by x, by x minus 2, because we know x minus 2 has to be a factor because one of the roots is 2. So if you multiply this by x minus 2, you then get your cubic, which then means we know what c and d are. Okay, that's it. I hope that wasn't too fast. Please let me know if there are any of those slides you want me to go through in any detail.